we're going to revisit the problem of finding the area underneath a curve. For this to make sense, the curve should live entirely above the x-axis, and what we learned in Calc 2 is if that curve is the graph of some function, in this case the function capital F of x, and we have the graph of f lying above the x-axis, so capital F is a positive function, going from x equals a to x equals b, the area is just given by this definite integral, the integral of from a to b of f of x dx. The question today is, how do we find the area underneath a curve when that curve is given by a parametric representation? In other words, we have two parametric functions, f of t and g of t, f of t defining the x-coordinate, g of t defining the y-coordinate, where t runs from alpha to beta. So I've set this up so it's the same curve as before, but we have this parametric representation. Before we talk about the area underneath the curve, in order for that to make sense, we need our y-coordinate always positive so that the curve lies above the x-axis. So we can talk about the area beneath the curve and above the x-axis. And we need the curve to be moving from left to right, and in order for that to happen, we need f prime of t positive. That means the x-coordinate is always increasing, moving left to right. Under these situations, I have it set up where the beginning point of our curve, f of alpha, g of alpha, is this point here. That corresponds to the x-coordinate, x equals a, as we had used before, and the x-coordinate at the end here, f of beta, is just something we'll call b. To find the area of the curve, we can just do what we did before and integrate from a to b. The y-coordinate, here we're thinking of y is some function, capital F of x, dx. But we don't know what capital F is. We could find capital F if we could eliminate the parameter, but our question is, can we find the area underneath the curve without eliminating the parameter? We could just express it as the integral from a to b of y dx, but how would we compute that? Well, I claim we can compute that just by integrating over the parameter t, from t equals alpha to t equals beta, and what we have to integrate is g of t times f prime of t. You can think of that as g of t is just y, and f prime of t is just dx dt. So then we're integrating from alpha to beta of y times dx dt dt. Our question now is, why does this work? Why is this integral the same as this integral, which gives us the area that we desire? The answer is, we can show that those two integrals are the same just by a substitution. In this second integral, if we just let x be little f of t, which is what we have in our parameterization, then of course dx is just f prime of t dt. And if we want to transform this integral below into an integral involving x, how would we do it? Well, we would just replace the f prime of t dt by the dx. The g of t gives us our y-coordinate. And how would we change the limits? Well, when t equals alpha, x equals a, and when t equals beta, x equals b. So this integral below transforms to exactly this integral above, which we already know is the area we desire. And that's what tells us we can just use the parametric representation. We do not need to eliminate the parameter and find y directly as a function of x. We can just integrate from alpha to beta, g of t, f prime of t dt, and get the area directly from the parameterization. Here's an example. Let's say we have a curve given by this parameterization where x equals t squared, y equals 3t minus 1, where the parameter t runs from 1 to 3. It's easy to check that y is always positive in this region, and certainly dx dt is positive, so that we're moving to the right along the curve. And if we draw the curve, it has basically this shape. We could plot a few points. The initial point when t equals 1 is the point 1, 2. The end point when t equals 3 is the point 9, 8. And the question is, how do we find the area underneath this curve? Well, using the formula we derived before, The area is just given by the integral over the range of the parameter from t equals 1 to t equals 3 of 3t minus 1, that's our g of t, times f prime of t, the derivative of our function little f of t, that's our x-coordinate, dt. And this is then a very simple integral to evaluate. That's the integral from 1 to 3 of 6t squared minus 2t, that quantity dt. Anti-differentiating and evaluating at the limits tells us that area is exactly 44. Now, there are other ways we could solve this problem. One way is just to express this curve as some function of x. And to do that, we would have to eliminate the parameter. So how would we eliminate the parameter? Well, I'll show you that here. To eliminate the parameter, one nice trick is to take one of the variables, say x, which is t squared, and solve for t. T is just the square root of x. If I plug that into the other equation, we get y is 3t, which is then 3 square root of x, minus 1. So when we eliminate the parameter for this curve, we get y equals 3 square root of x minus 1, which means that this entire curve is part of the graph of this equation, or this function 3 root x minus 1, and that's what I've shown here. It's the exact same curve we had before, but now we've just expressed it differently. And of course, we can find the area under the curve just by integrating. In this case, we want to integrate from x equals 1 here to x equals 9, this function of x dx, and I'll leave it to you to check. You should be sure you're comfortable evaluating this integral, and you get exactly the same answer, 44.